Gauss law in its differential form is a very concise and precise way to define electrostatics. It is also very powerful. Gauss law can be used to determine the electric field very easily in symmetric situations. However, the question arises if Gauss's law alone is sufficient to define electrostatics. In differential form, Gauss's law looks like this. Divergence of the electric flux density at all points in space is equal to the charge density at that point in space. From that equation we would assume that if the charge density is 0, that we also get an electric field that is 0. Certainly if the charge density is 0 everywhere. Well, if we have a situation where we have charges here and a point of interest somewhere there, then of course we don't have 0 charge density in this point, but an electric field because of the charges, the source charges over here. However, if there are no charges anywhere, we would also expect that everywhere in space the electric field is 0. Is that necessarily the case? Let's check that. An electric field might be defined like this. Electric flux density is equal to some calibration constant d0, which determines the magnitude of the field, and then it depends on the x, y and z coordinate in the following way. Minus y gives us the x coordinate, x gives us the y coordinate, and in order to keep it simple we keep the z coordinate always 0. In vector notation we then have d0 times minus y, x and 0 as the definition of our vector field. If we work out some of those vectors in space in an x, y coordinate system, for example we obtain for the position 1, 0, 0, which is this position, x coordinate equals 1, y and z are 0, we obtain that the field vector is 0, 1, 0, and that gives us this vector here. Similarly, if we go to position 0, 1, 0, 1 on the y-axis, which is up here, then the field vector is d0 times minus 1 in the x direction, minus 1 in the x direction, but 0, 0 for y and z, which gives us this vector. And very quickly one can see that this kind of rotational field arises. Now, in order to check if this is an electrostatic field, it needs to be in agreement with Gauss's law, and we should work out what the divergence of D would yield in this case. The divergence of D in this case is equal to the first partial differentiation of the x component plus first partial differentiation of the y component with respect to y plus the first partial differentiation with respect to z of the z component. If we carry this out, we find that dx with respect to partial differentiated with respect to x gives us a 0 because there is no x dependence, so we get a 0. Similarly, if we differentiate the y component with respect to y, because there's no y dependence, we get a 0, and the differentiation of 0 is also 0. So we find that the divergence of D is 0, and in fact everywhere. Divergence of the field is everywhere 0. Now this is fully consistent with Gauss's law, but in contradiction to experience, because we don't have any charges, but still we have a vector field. That's not what happens in electrostatics. Without any source charges, there isn't a field. This indicates that Gauss's law alone, Gauss's law alone is insufficient to rule in or rule out a vector field in electrostatics. Some of you will know that such a vector field, such an electric vector field, can indeed exist, but not in static electromagnetism, but in time-dependent electromagnetism, because changing magnetic field can indeed create such rotational electric field. But at the moment we're looking at static situations, and in static situations, in electrostatics, such fields should not exist, certainly not if there is no charges that are the sources of this field. So our foundations of electrostatics so far is not sufficient. We need an additional requirement. The most obvious feature of this odd vector field, which we think should not exist in electrostatics, is that it curls. And it is indeed the curl, the fact that field lines fall back on themselves, that is inconsistent with electrostatics, because experience tells us that in electrostatics field lines have a beginning at a source and an end at a sink. So it is this curling of the vector field that we can use to exclude fields like this which are not part of electrostatics. In order to determine the curl of a vector field, we can use the curl operator. The curl of a vector field mathematically is defined by this determinant, whereby we get 6 terms. We differentiate all 3 components of the vector field with respect to the respective other 2. That gives us 6 terms, and some of these terms give us a positive sign or have a positive sign in front, and some of the other 3 of the terms have a negative sign, a minus sign in front. And this determinant explains how this comes about. We might just quickly do this to illustrate. So we get the following term. We have for the following 3 terms. For the x component of the result, so the curl of a vector field gives us another vector. So we produce another vector, and the x component of that vector will have a positive dy of the z component of the original vector. And then we have a minus, whereby we are differentiating the y component with respect to z. For the y component, we obtain positive dz of vx and negative dx of vz. And then finally for the z component, we have positive dx of vy minus, that's this one I've indicated in red here, dy of vx. That's the general definition of the curl operator. If we apply that to our case here, we obtain the following. So the curl of our example vector field D is a vector, and it has an x component where we have to take dy of vz, that's a 0. Then we have to take dz of vy, that's also a 0. Then we have to take dz of vx, that's a 0. Yeah, there's no z dependence in the x component. Dx of vz is a 0 because there is no x dependence in the z component. Dx of vy, this is vy, dx of vy, that produces a 1. Yeah? Partial differentiation of x with respect to x is 1. Dy of vx produces a minus 1, and because there is a minus sign we get a plus 1. So we obtain that the curl of our example vector field D is equal to 0, 0, 2. So it has a finite, we have a finite vector pointing in the positive z direction. And indeed that's what we might expect, because the field curls. So we have a vector pointing upward like this. Since this is not an electrostatic vector field, the natural conclusion is, in order to exclude rotational curling vector fields like this, we have to require that for every electrostatic field, it has to hold, it has to be true that the curl of that field, the curl of D, which then is equal to the curl of E, has to always be 0. If that is the case, we can exclude curling vector fields and possibly define completely vector fields in electrostatics. And that's indeed the approach, and that is the definition of electrostatics. So in addition to Gauss's law, in addition to Gauss, we require that the curl of E of an electrostatic vector field is always 0.